Good morning, everyone. I am K. Narsimurthy, working as an assistant professor in the Government First Aid Women's College, Tumkur. I am going to present the video for the course BSc, and the subject is physics. And the paper which I am discussing today is semiconductor devices, digital electronics, laser, and fiber optics. In that, the topic which I am discussing is the number system. Now today we are going to learn the different kinds of number system which come across in the digital electronics, and we are also going to learn about the conversion of the number system, one number system to other number system. In the digital electronics there are two ways of representing any physical quantities. One is analog method, another one is the digital method. In the analog method, the quantity that are represented by a voltage or a current meter movement that is proportional to the value of quantity. I can give you an example for the analog this measurements. You have seen the wall clock. So wall clock will have a needle, and that time is proportional to the movement of that needle. So you have seen the speedometer in your vehicle, in your mopeds. That speedometer needle will shows you how much speed you are going. The quantity is proportional to the value of the meter movement. That is the way we represent the analog quantities. Of course, we have in our laboratories the analog voltmeter is there, where the voltage is measured with the needle movement, and we have an analog ammeters to measure the current with the meter movement. We are still using so many analog quantities in the laboratories and also in the day-to-day life. And the other way of representing any physical quantity is the digital method. Here in this method, the quantity is not at all represented by the proportional quantities, but it is represented by symbols. So here now we have a digital meters on our car or on our mopeds. When you look at the speedometer, digital speedometer, just it displays the number. If you are going with a 60 km per hour, it displays 60 km per hour. Directly it shows the number. In the wristwatches, we have a digital watches nowadays. In the wristband, it directly tells you the time. If it is 10:50, you need not analyze the needle movement here. In the digital representation, it directly shows the number. Okay, here there is no proportional quantities, here there is no needle movement, it directly shows the symbol, and the symbol is the number. These are the two methods where we express any quantities. We have analog circuits and we also have a digital circuits. These analog circuits and digital circuits are used for transmission and the process of the signals like sound and light. Light and sound signal can be transmitted through these digital circuits and the analog circuits. But when you look at the analog circuit, it directly takes the signal and it do the processing or it transmit, and the output will also be the analog signal. You don't need to convert this. But whereas in the digital signal, it only accepts the digital signal. It will not directly take this light wave or a sound wave. Again, you have to convert this wave into a digital signal, and the digital circuit will do the processing, and the output will also be the digital. Again, in the output also you have to convert from digital to analog. I can make out some differences of the digital and analog circuits. The analog circuit operates on a continuous valued signal. So it operates on a continuous value signal, whereas the digital signal functions on the signal that exists in a simple two level. Simple two level means it's an on level and off level. That is zeros and ones. It operates only with the zeros and ones. That is the speciality of the digital circuits. Whereas in the analog circuit, you don't need to change any input. It takes the input as such and do the logical processing, and it gives you the output as an analog signal. Whereas in the digital circuits, it will not directly take the analog signal. Again, you have to convert this analog to digital and again the digital input it takes and do the processing and gives the output again in the digital form. Again in the digital form has to be converted into analog form. That is the two major difference between the analog circuits and the digital circuits. Now we move on to the number systems. We have a different kinds of number systems. As I mentioned, there are decimal numbers, binary numbers, octal numbers, hexadecimal numbers. These are the four different kinds of number system we know. We know one by one. We will learn one by one. First thing is the decimal number system. Decimal number system is expressed as units of tens, hundreds, and so on like this. The currency which we are using is in the decimal number system. We give 10 rupees, we give 100 rupees, we give 1000 rupees. That's a decimal number system. Here the subscript is 10. It's called the base, or it's also called radical. But whereas in any decimal number system, the left digit, I have given you the example of 8674, 8674. The leftmost digit, which is 8 here, and this leftmost digit has a greatest value, greatest weight, and is called most significant digit. This 8 is the most significant digit, and the rightmost digit, which has a least weight, because it is in the units, so it has a very least weight, and this 4 is called least significant digit. The 8 is called most significant digit, the leftmost digit, and the rightmost digit is called least significant digit, LSD, and the leftmost digit is called MSD. Okay, so this is the way we represent the decimal number 8674 within the parenthesis, and the base is 10 here. This is the decimal number system. We move on to the next type of number system, which is binary number system. Here the computer circuits requires only the binary number system, because they will not process a decimal number system. They needs the input as the binary form, inputs in the binary form, so one needs to understand this binary number system carefully, so that because it's the only input for the computers for processing. Okay, in this binary number system only two digits are used, that is 0 and 1. Only two digits are used. Weight or place value of each position can be expressed in power of 2. You will come to know when I take an example. So here I have taken an example within the parenthesis 1010 within the parenthesis, and base is 2. Okay, so this is the binary number which I have taken as an example, 1010. We are using only 0 and 1. Here in the binary number system, the 0 represents or 0 corresponds to low, false, open, no, down, cold, south, off, and so on. But this 1 corresponds to the opposite thing, the other thing, the high, true, close, yes, up, hot, north. Okay, so yes, the 8-bit word is a byte. We call this 8-bit word is a byte, and 0 or 1 is a bit. Okay, so 0 is in 1 bit, 1 is also in 1 bit. If you make a group of 8 such bits, it is called a byte. Okay, now we move on to the conversion of one number system to another number system. First we look into the conversion of binary number system into a decimal number system. Binary number system can be converted into a decimal number system just by multiplying each bit by its position value or a place value and then adding all together. Okay, exactly we are doing with an example. I am showing with an example. I have taken an example as this one as 110101.101, very lengthy binary number. Okay, this has to be converted into a decimal number. It's a very simple method. Each each binary number is multiplied by its position value. See, it's 1, 2, 3, 4, 5, 6. It's in sixth position. Sixth position, its position value is 2 power 4. It starts from 2 power 0 and then 2 power 1, 2 power 2, 2 power 3, 2 power 4 and 2 power 5. Sixth position is 2 power 5. Now this 1 multiplied by 2 power 5 and the second digit is again 1 and that is multiplied by 2 power 5 and the third digit is 0. This is multiplied by its place value, that is 2 power 3, and the fourth digit is 1. It is multiplied by 2 power 2 and the fifth digit is 0. It is multiplied by its weight or place value, it's 2 power 1, and the next digit is 1 and it is multiplied by 2 power 0. And after decimal, the place value, it goes like this. Its place value goes like 2 power minus 1, 2 power minus 2 and 2 power minus 3 and so on. Now we have only 3 digits after the decimal point. So 1 into 2 power minus 1, 0 into 2 power minus 2 and 1 into 2 power minus 3. You have to be very careful. After decimal point, the place value of each digit goes like 2 power minus 1, 2 power minus 2 and 2 power minus 3 and so on. Okay. Now all these are summed together. All these are added together. These are the multiplication values. If you sum it together, I'll get the value as 53.625 and this is the decimal number which is equivalent to the binary number, that is 110101.101. That's an example I have taken. Okay, I have taken another example also. The example 2 is 10110.1110. It's again the same procedure. Taken each digit, multiply its place value or and weight. Okay, then sum all this together. You will get a decimal number which is equivalent to the binary number. Now we learned the conversion of binary number to decimal number. Next we look into the conversion of the other thing, which is decimal to binary conversion. Okay, in this method, a given decimal number is divided progressively by 2. The given number is divided progressively by 2 and remainder is written down after each division. Okay, and the remainder is taken in the reverse order. Reverse order in a sense, you have to take from bottom to top to get a required binary number. It's a very simple method. It's called double dabble method. Okay, so each time you go on dividing by 2, write down the remainder and take the remainder in the reverse order, that is from bottom to top. I have given you an example, that is 25 is the decimal number base 10. Now I am going to divide 25 by 2 successively. So once I divide, 2 12s are 24, remainder is 1. Write down the remainder each time. Again the 12 is divided by 2, 2 6 are 12, remainder is 0. Again write down the remainder. Again this 6, 2 3s are 6, remainder is 0. Write down the remainder. Again this 3 has to be divided by 2, 2 1s are 2. Okay, write down the remainder. This is 1. Now you write down all the reminders in the reverse order, that is from bottom to top. You will get a binary number equivalent to that decimal number. Now the answer is 11001. This is the answer. This is the binary number equivalent to the given decimal number 25. I have given you another example. Example 2 is 16. Again the 16 is divided successively by 2 and remainder is written down and remainder is taken in the reverse order, and that will gives you the desired binary number or an equivalent binary number given for the given decimal number. This is a very simple method. We learned the conversion of decimal to binary as well. Move on to the next type of conversion. This is entirely a different thing. Decimal fraction to binary fraction. It's a separate category because the method that we use for converting the fraction here is different. Decimal fraction to binary fraction. Here decimal fraction can be converted into binary fraction by a rule called multiply by 2 rule. Okay, yeah, each bit is multiplied by 2. Each bit is multiplied by 2 and carry is recorded in an integral position. These carries taken in the forward direction, be careful, not the reverse order. Now it is taken in the forward direction, means top to bottom, gives the required binary fraction. Okay, with the example you can understand better. I have taken the example as 0.45 and the base 10. That's a decimal number, decimal fraction. Multiply it by 2. Multiply the given fraction by 2. If I multiply that by 2, the answer is 0.9. Look at the integer part here. Integer part is 0. Write down the integer part here. If it is 0, write down 0, no problem. Okay. In the next step, take this 0.9 and again multiply it by 2. The answer will be 1.8. So look at the number digit in the integer part. It is 1. Write down the number which is in the integer part, 1. Again, after that, after writing down, we left with only 0.8. This 0.8 will be taken to the next step. This 0.8 has to be multiplied by 2 again. Okay, but don't take 1.8. You just take 0.8 because the integer 1 has already written over there. Now we left with only 0.8. Take this 0.8, multiply it by 2. It will gives you 1.6. Again write the integer. Now if you write the integer, we left with 0.6. Take this 0.6, multiply it by 2 again. It will gives you 1.2. The remainder is 1. Now we left with 0.2. Multiply again by 2, 0.4. Now the integer part is 0. Again write down this 0. But answer will be, writing the answer, you have to be very careful. You have to write from top to bottom, that is in the forward direction. Top to bottom means it is 0, 1, 1, 1, 0. Okay, but be careful, you have to write it after this decimal point. It's 0.01110 to the base 2. This will be the answer. This will be the binary fraction which is equivalent to the given decimal fraction 0.45. Okay. Right. Next we'll move on to the next type of conversion, that is decimal to octal conversion. Okay. In this method, a given octal number is divided successively by 8. Just like how we did successively by 2 in the binary case, exactly in the same way we are doing here, means we are doing successively by 8 here. Okay. And the remainder is written down after each division. Exactly the same procedure. This remainder is taken in the reverse order again. Reverse order, that means from bottom to top will gives you the required binary number. Okay. With an example you will understand very clearly. The example is 98, that's a base 10. This 98 has to be divided successively by 8 because this is decimal to octal conversion. You have to divide it by 8. Okay, so 8, if you do it 8 12s are, the remainder is 2. Again for the 12, again you have to divide by 8, the remainder is 4. Now you take this in the reverse order, the answer will be 148 to the base 8. Okay, so this is how you can convert a decimal number into an octal number. Now the possible numbers that we use in the octal number system are 0 to 7. That's 0, 1, 2, 3, 4, 5, 6, 7. These are the 8 digits which we use in the octal number system. Now we will see the conversion of octal numbers system to decimal number system. It's a very simple thing. If a decimal number is given, means if an octal number is given, multiply each octal digit by its weight or a place value and add the resulting product. Okay, exactly how we did in the binary conversion of binary number system to decimal number system. There we have again we have multiplied with the place value and we added the resulting product. So the example which I have taken is 64.12, the base 8. 6 is the first digit, and its weight or place value is 8 to the power of 1, and the second digit is 4, and the weight is 8 power 0, and after the decimal the digit is 1 and the value is 8 power minus 1, and this 2 8 power minus 0 minus 2. Again, if you sum all these things together, you will get a decimal number which is equivalent to the given octal number, and the answer is 52.1562. That's a decimal number, and that is the answer for that problem. Now we look at the conversion of decimal fraction to an octal fraction. Fraction is a different category because we use a different method for converting a decimal fraction to an octal fraction. Again, it's a very simple method. Each bit is multiplied by 8 and the carry is recorded in the integral position. And these carries are taken in the forward direction, that is from top to bottom, gives a required binary fraction. Exactly how we did conversion of decimal fraction to a binary fraction, exactly is the same method we are using here in the octal number system. See, the problem given here is 0.24, and this number, given number, is multiplied by 8. It becomes 1.9. Integer part is 1. Write down that integer part, and we left with 0.9. Again, you multiply 0.9 by 2. We left with 7.2. Write down 7, and 0.2 again multiply by 8. 1. Again multiply 4. Again multiply 6. That has to be written in the forward direction, top to bottom. The answer will be 17146 to the base 8. That is the answer. That is the equivalent, that is the octal number equivalent to the given decimal number. Now again, another kind of conversion, it's octal to binary. Octal to binary is entirely a different procedure. Here, a given octal number system, each digit in the given octal number system is converted into a binary equivalent. Be careful, each digit, each bit has to be converted into binary equivalent. So if we look at the example, it will be very, very clear. Example is 23. That is the given octal number, 2 and 3. Here the each octal digit, the first octal digit is 2. That has to be converted into binary equivalent. So 2, the binary equivalent is 10. How will I get this 10 is, you divide that successively by 2. It will gives you the binary equivalent number. So binary equivalent number for 2 is 10. We are grouping it as 3. So add 0 here. So it's 0, 1, 0. Very simple thing. Again, the binary equivalent for 3 is 1, 1. How I get it? Multiply by 2. Write down the remainder. Take the remainder in the reverse direction. It will gives you 1, 1. Make it 3. Group of 3. Be careful. You have to write as a group of 3 here. Okay. So you put 0 to the left side. No problem. Don't put the 0 to the right hand side. Put the 0 to the left hand side. So 0, 1, 0. Here it is 0, 1, 0. Here it is 0, 1, 1. Write down all the things together. Write down together. Together it will be 0, 1, 0, 0, 1, 1. That is the binary equivalent number to the given octal number. Now, if I look at the second example, 34.562, we have a decimal fraction also. We have an octal fraction here. Again, the same procedure for the fraction. First digit is 3 and the binary equivalent is 0, 1, 1. Second digit is 4 and the binary equivalent is 1, 0, 0. Point, you retain the point as it is. 5 binary equivalent is 1, 0, 1. 6 binary equivalent is 1, 1, 0. 2 binary equivalent, but you have to mention as a group of 3. So put 0 to the left hand side. It will be 0, 1, 0. So write it together. Don't submit. Write the digits as it is together. If you write it together, it is 0, 1, 1, 1, 0, 0, 0.10110010. It's a very lengthy number, lengthy binary number, which is corresponds to a given octal number. This is how we can convert an octal number to a binary number. Next is a binary to an octal conversion. If a binary number is given, first thing we have to do is we have to group it. Group in such a way that you have to group the binary number in threes. Three numbers you have to group. Starting from the binary point, you have to grouping has to start from the binary point, not from the left side, not from the right side. You have to start from the binary point. Okay, then convert each group of 3 to an octal equivalent, okay. So if necessary, zeros are added. Okay, right. I'll with an example I can explain you better. Okay, this is the example. 1011 is the integer part, and after the decimal we have 01101. Okay, first thing you have to group the number in threes. Okay, grouping has to start from the decimal point. Here, if this is the decimal point, you have to start grouping from the decimal point 110. That is done. Okay, if we left with only single one here, and you have to make it 3. Add zeros, no problem. Add 2 zeros. 001. This is a group of 3 binary, and this is a group of 3. After this decimal point, okay, again take 3 digits, 011, group it. That's my first group, and we left with only 2 digits. After that, you cannot group a 2 digit, make 3. How will you make it? Add one more 0. Okay, so it is 010. So first thing is to group the given binary number in threes. The grouping has to start from the decimal point. Okay, so we are done with that. Now you convert each group into an octal equivalent. Okay, this 001, the octal equivalent is 1. 011, the octal equivalent is 3. 011, the equivalent is 3. 010, it is 2. The answer will be 13.32 is the octal number corresponding to the given binary number. We move on to the last number system, that is an hexadecimal number system. This hexadecimal number system has some different features. This is extensively used in the microprocessor work, and this is a much shorter number compared to a binary number. Binary number is a very lengthy number. Compared to that, this hexadecimal number is too short, so that it's easy to write and remember. These numbers 0 to 9, and after that we use an alphabets A to F. Okay, just like we use 0 to 9 digits, and after that 10 we will not represent 10. Instead of 10 we represent A, alphabet A. For 11 we represent B. For 12 we represent C. For 13 D. For 14 E, and for 15 F. There ends. Okay, up to 15, 0 to 15. Now after 9 we represent alphabets A, B, C, D, E, F. Okay, so these are the hexadecimal numbers, 0 to 9 and A to F. Totally 16 numbers. These 16 numbers are hexadecimal numbers. Now we'll see the conversion of the hexadecimal to binary, then octal, then to hexadecimal. We look at all these conversions. First conversion is hexadecimal to binary. A given hexadecimal number can be converted into binary number, but each hexadecimal digit has to be converted into 4-bit binary equivalent number. Okay, right. Here is the example 9AF. Each digit of hexadecimal, the first digit is 9. Write the equivalent binary number for this 9, but it has to be number of 4 bits. It has to be 4-bit number. 91001. A means what? A is 10. Okay, it's 1010, and the F is 15. So for that it is 1111. Okay, so write it together. You will get an answer. You will get a binary number equivalent to this given hexadecimal number. Very simple thing. each hexadecimal digit has to be written in terms of 4-digit binary equivalent number. If it is not a 4-digit, make a 4-digit by adding 0 to the left hand side. So here is another example. C5E2 is an hexadecimal number. C, write the binary equivalent. For 5, write the binary equivalent. For E, write it. For the 2, you will be short of 2 digits. Add 2 extra zeros to the left hand side, you will get a 4-digit binary number. Then it's a very simple thing. It's not an adding, it's write down these numbers together. If you write all these 16 numbers together, it will gives you a binary number which is equivalent to that hexadecimal number. Now the conversion of binary to hexadecimal conversion. Now here is, you have to group the bits in 4s. 4 digits you have to group. Again, how will you group? Grouping starts from the decimal point. If you are short of digits, if you don't have a 4 digits, add zeros to the left hand side in the integer part. If it comes to a decimal fraction, add 0 to the right hand side. Simple thing. Okay, right. And each group has to be converted into a hexadecimal equivalent. Now I have given you an example of 8 digits. It's a very simple to group. 4 digit you can group it very easily. No extra zeros you require. 1000 is the first group. The equivalent hexadecimal digit is 8. Okay, and the second group is 1100. And 110 is A is 10, B is 11, C is 12. So 1100 is 12. You cannot write 12 in the hexadecimal number system. So instead of 12, you have to write C. Okay. Now the answer is 8C. 8C is the hexadecimal equivalent corresponding to the given this binary number. Here is another example. Now grouping is again easy here because we have 8 digits in the integer parts, again 8 digits in the decimal parts. Very easy to group of 4s, group a bits in 4s and convert each group into an hexadecimal number. Okay, we look into the next conversion. Next is a conversion of hexadecimal to a decimal number. Okay, so to convert an hexadecimal number, just multiply each hexadecimal number by weight and add the resulting products. Exactly how we did in conversion of binary to decimal and octal to decimal. Exactly in the similar way we are doing here conversion of hexadecimal to a decimal. But place value or weight will keep on changing with the number system. Here is the given hexadecimal number F8E6.36. The first digit is F and the place value is 16 power 3. You multiply F with the 16 power 3. You should know that what is F here. F is 15. 15 into 16 power 3 and 8 into 16 power 2. E means 14 here. 14 into 16 power 1 and 6 into 16 power 0. There ends the integer part. You have to move on to the decimal part, fraction. After the digit point, the first digit is 3. 3 into 16 power minus 1 and the next digit is 6. 6 into 10 to the power of minus 2. You calculate all these things and sum all the resulting products. If you sum all the resulting products, I'll get the answer. This answer is the decimal number which is equivalent to the given hexadecimal number. Now we still have a conversion of decimal to hexadecimal number. Here again the same method how we did in decimal to octal, decimal to binary, exactly in the same method, but here it is 16. There it is 8 and 2, but here it will be 16. Divide a given number successively by 16 and write down the remainder after each division, and reminders are taken in a reverse order from bottom to top. You will get a required hexadecimal number. Here is an example. 2479 is an example. 2479, divide this by 16 and the remainder is 15 here. Don't write 15 because 15 is not an hexadecimal number. So 15 instead of 15 you have to write F here. Okay. Again one more division you can do here. After one more division, the remainder is 10. Don't write 10. 10 can be represented as A in the hexadecimal number system. Write it as A. Okay. Now we left with the 9 here, A and then F. Be careful, you have to write it in the reverse order. Okay. So it is 9, A, F will be the answer, will be the hexadecimal number equivalent to a given decimal number. Move on to the yeah. These are the different number systems, and we learned the conversion of one number system to another number system, and these are the very simple mathematical methods. Lot of different procedures are there in this conversion, but all are simple, all are different methods. So once you learn this method, the solving any number of problems will be very simple. Okay, so you can refer some good number of books here. Basudev Ghosh is a very good book for the principle of electronics, and one more book is written from the Tumpur University people, and that's a fundamentals of physics. Another old book is the Malvino and Leach, and that is for the digital principles. It's a very good old book. And there's another book which is very old for degree students, and this is a Sundarajan book. And there also you can find some of the elements of digital electronics. And of course in the internet also you can get a very large number of data, but you have to select which is correct and which is wrong from the internet. Okay, so these are some of the references you can go through, and thank you very much.